Hello and welcome. In this video, we're going to take a look at a new technique of integration. And this technique is going to be most often applied when you see a product of two functions in your integrand. And so it kind of starts off by taking a look at how we involve the product rule for differentiation rules. And then we can reverse that product. So let's take a look at the product rule. We will start off with the basics. Here we have the derivative of a function f times a function g. And we remember that when we're looking at the derivative of a product, we actually have a very interesting form, f prime g plus g prime f. Now, with that in mind, we can start to come up with an integral formula by integrating both sides with respect to x. Now, if we are integrating the left-hand side, we see that the derivative of fg is then being integrated, and that should cancel out by the fundamental theorem of calculus. And that would be the fundamental theorem of calculus part 1. Now, at this point in time, we've got a formula that involves integrals. So if we rearrange that, we can have one integral on one side of the equation and a different integral on the other side of the equation. And this is how we're going to use integration by parts. If we are given an integral of this form on the right, then we can replace it with an equivalent expression on the left-hand side that involves a different integral. And we're really hoping that this is going to give us a new integral that is easier to evaluate. So written in its most common form here, the integration by parts formula is when we have the integral of a function f of x times another function that is the derivative of g, all with respect to x. We'll replace that with the expression f of x times g of x minus a new integral g times the derivative of f with respect to x. And the goal here of this new integral should hopefully be one that we can evaluate with one of the methods that we've already looked at. Now, this is a very common way to look at that formula in terms of two functions, f and g. But if we want to make this a little bit easier to remember and a little bit more compact, rather than using function notation, let's just invent two new quantities. Let's let f of x be just a quantity, we'll call it u. And let's let g of x just be a quantity, and we'll call that v. So u and v depend on x, and then we can kind of get the idea of how to compact this down using Leibniz notation. And so if we let u equal f of x and v equal g of x, then we can write our derivatives with Leibniz notation. Leibniz notation is where we would write the derivative of u with respect to x as du by dx, and of course that corresponds to the function notation f prime of x. And similarly, we can take the derivative of v with respect to x, and that would correspond to g prime of x using function notation. And now what we can do with each of those is rearrange them into the differential forms. Du would simply be f prime of x dx, and dv would be g prime of x dx, and that is how we get a very nice compact formula. Our integration by parts formula is now simply the integral of u dv equals u times v minus the integral of v du. Now, we've got the compact formula. We can bypass a lot of that theory now and apply this to integrals where we have a product. Now, the tricky part of integration by parts is deciding how we would choose the two components, the two parts of our initial integral. One part of our integral is going to be u, and one part of our integral is going to be dv. And these two parts will form the product. U is going to be needed to be differentiated to find du, and dv is going to be needing to be integrated to find v. That gives us a little bit of an inspiration of how we choose u and dv. So our original integral has u and dv, and our new integral has du and v. And so one of the goals here is to make this new integral easier. So try to strategize this so that the new integral v du is going to be easier than the original integral. And so of course that's one very major point of using integration by parts. But we kind of understand that antiderivatives are harder to evaluate than derivatives. So this process here on the right is definitely a harder process than this process on the left. That means that when we choose our u and v, we should be choosing that dv so that v is easy to calculate. With those two strategies in mind, let's make sure that we kind of come up with a priority list. Think of things for u that are easy to differentiate. but would be really bad choices of things to try to integrate. And so here on this table on the right, these are sort of a priority list of things that I would much rather look for the derivative of than integrate. So if you have multiple functions that form a product in your integral, it is best to choose u from this priority list, top to bottom. So that if you have multiple functions in there, logarithms are great when we take their derivative. The derivative of the logarithm of a function ends up becoming 1 over that function times the derivative of the inside. That's much easier to work with than integrating a logarithm. Inverse trigonometric functions, well, they have some messy derivatives occasionally, but integrating inverse trigonometric functions are going to be significantly worse. Algebraic functions, like even just a basic power x cubed, if we take its derivative, 3x squared, is simply going to be just 1 power less, which might make for an easier new integral. But integrating algebraic functions like x cubed would give us 1/4 x to the 4. And that's a higher power, and chances are that might not make anything easier for us. Trigonometric functions, let's say in our original integral we have a sine function. Taking the derivative of a sine function, it's just going to get us a cosine function. That might not make much of a change in our new integral to make anything easier. So it's a little bit lower down the list. And exponential functions, well, they're easy to integrate. That's not even a problem at all. E to the x is easy to integrate. The derivative of e to the x is unfortunately still e to the x. So choosing u to equal e to the x means that our du is still e to the x. That's not really going to make anything easier in our new integral. Keep this in mind. We can try to remember a general strategy for finding u, starting with logarithms, inverse trigonometric, algebraic, trigonometric, and exponential functions, or Lie8. Now, let's try a few examples and see if that strategy will generally work for us. In this first example, x ln x, we have two functions multiplied together, x and the natural logarithm of x. So it makes sense to just see whether or not a substitution is going to work. Substitutions can often work when we see a function multiplied by its derivative. When we see a function multiplied by its derivative, then simply having u equal to one function will give us the derivative of that function dx, and sure enough, we can just rewrite this as u du. And that would be an easy case of a product. But in this case, if we let u equal x, then the derivative of x is just equal to 1. And we are stuck with a logarithm in our integral. And if we let u equal the natural logarithm of x, then the derivative is 1 over x. And that is not going to cancel out the x that we also have as our second factor. So, in this case, this product is better to be tackled with integration by parts. Now, in integration by parts, we need to decide which of these two functions is going to equal u, and which of these two functions is going to be part of our dv. And the choice here, you can think of that Lie8 as being a nice guide, but if you want to just build up your intuition, u should be a function that we would rather differentiate, and dv is going to be a function that is possible to integrate. And if we don't know the integral yet, or antiderivative of the natural logarithm, then it makes a lot of sense that the natural logarithm is going to be our choice for u. If we let u equal the natural logarithm of x, then that means dv is going to be everything that is remaining in our integrand. That's x and dx. And now we start with u and we find its derivative. Du by dx is 1 over x, and it's better to rewrite that so that we have du. And that middle step can be skipped. We simply want to get this into differential form in the first place, and it's much easier to just do that in one single step. Now, this dv over here needs to be integrated. And we could write that step down if we wish, simply because integrals can take multiple steps here and may be a little bit trickier to do. But we will always get the integral of dv on the left-hand side, which is just simply v. It's a 1 in the integral, and the antiderivative of 1 would be v. Now on the right-hand side, the antiderivative of x with respect to x would be 1/2 x squared. And it's at this point in time that we would often write our plus c. But this isn't really the problem that we're even trying to solve. This is simply just an antiderivative that we are going to replace with our new integral that we're still going to be having to solve. we'll get our plus c, our arbitrary constant, eventually. In this case, again, the antiderivative of x is fairly simple, and you may not even have to write that step. So our new integral is going to be involving 1 over x dx multiplied by 1/2 x squared. These are much easier to multiply together to form a better integral. So according to integration by parts, u times v minus the integral of v du. And now if we simplify, hopefully this leaves us with an integral that's much easier to work with. And sure enough, x squared over x is simply just equal to x, and we can find the antiderivative of this new integral. And it's at this point in time that we do need to include the arbitrary constant of integration. Now in this next example, we're simply just integrating the function arctangent of x, or inverse tangent. And you'll see it doesn't really look like a product. But nonetheless, we're still pretty stuck if we don't know the antiderivative of arctangent. So we could try a substitution, but there's only a single function here. There's really nothing we could substitute that would make this any easier. Remember that a simple substitution like u equals x is never going to do anything. We really only do substitution when we sometimes see a function with its derivative kicking around. And that's not going to happen here. So how do we turn this into a product? Well, we have to be a little bit creative. Arctangent of x is a function that we should know the derivative of, even if we don't know the antiderivative. It makes a lot of sense to let this equal u. But that actually does leave us with a product, because now we can always have 1 dx. And we do know how to find the antiderivative of 1. Now, with those u and v functions defined, let's see what this new integral is going to turn out as. Well, we have uv, and it's often a lot less confusing when we put our algebraic functions prior to trigonometric and inverse trigonometric functions. And then we subtract and have a new integral with the form v du. Well, x times 1 over x squared. That can just be written as x over 1 plus x squared. All right, well, this may not be exactly the easiest integral yet. We still have to do some work on that. You see here, we're at least at a point now where we might be able to use a substitution. If we can find a function that is involved in this expression, and its derivative is a factor of that expression, then a good substitution should exist. And let's choose capital U, since it may be confusing to use u twice. We'll use capital U as 1 plus x squared. Now remember, with substitution, we are going to change variables, and we'll have to change back for indefinite integrals. If this is a definite integral problem, then we can simply change the interval of integration, and we won't have to change our variable back at the end. Here we're going to have to change this to du equals 2x dx in differential form. And if we like, du over 2x is equal to dx. And you can see how this is going to cancel the x in our expression. What we really want to see here is that all of the x's are eliminated from this expression, and we end up with an expression in terms of just the new variable. Well, we have a 1/2 that can factor out, and we have the integral of du over u, which is just the same as 1 over u du. We know the antiderivative of that expression is the logarithm of the absolute value of u. And from there, we also need to make sure to include our arbitrary constant of integration, and then we will plug in our u equal 1 plus x squared again. Now, if you wish, you can actually take a look at the absolute value symbol here and see whether or not it's even necessary anymore. Because our u was equal to 1 plus x squared, and we know x squared is always going to be greater than or equal to 0, then our u equal 1 plus x squared is always greater than or equal to 1, and its absolute value is simply still going to be 1 plus x squared. We won't have to ever worry about negating the expression to make it positive. So we could get rid of the absolute value here and just write this as simple parentheses. Now, with this example, you might be able to see that that general strategy Lie still applies, because the two functions I've created, since I've created this 1 there, that would be algebraic. It's simply just x to the power 0. It's a very small algebraic expression. And then we have an inverse trigonometric function. Well, inverse trigonometric functions are higher priority for u than algebraic expressions. So once again, that strategy Lie might help you out here. Well, why don't we try a definite integral and make sure that this whole method is still going to make sense when the result should be a value and not an expression. Okay, in this example, we've got a function x squared sine x that we're integrating from 0 to pi. You try that substitution right off the bat, and you take a look and find a function and see whether or not its derivative is going to be a factor. Maybe u equals x squared. That won't work because its derivative is 2x. And what are we going to do with the sine x? You could try u equals sine x, but then if that's the case, then the substitution will get you du equals cos x dx, and that's not going to work. But there is a product of an algebraic function x squared and a trigonometric function sine x. And you can think about which of those is going to be easier to work with as a function to differentiate and which is going to be easier to work with as a function to integrate. On our priority list, algebraic expressions are great for taking the derivative of as the power goes down, and that'll be a little easier integral on the other side of integration by parts. But u equal sine x, that's going to get us a new integral with cosine x, and integrating x squared is just going to get us x cubed over 3. That would mean our new integral would be x cubed over 3 cos x, and that's certainly not any easier. So sticking with the guide here, let's try u equal x squared. Differentiating that is going to be fairly straightforward, and our dv can equal sine x dx. Integrating that will give us negative cosine of x. Now, to this point in time, we are dealing with a definite integral. We're not going to have any plus c's to worry about, but we are going to have to evaluate all expressions from x equals 0 to x equals pi. So this uv that we get, that expression already will need to be evaluated from 0 to pi because it should just come out as a value. We're not looking for an expression in terms of x. Now, when we get to our integral, we see we are subtracting the integral of v du, but we have a negative sign here that's going to turn this subtraction into addition. And once again, this is an integral that has to be evaluated from 0 to pi. So we could go ahead and start evaluating this expression here on the left and just get a number, or we could wait till further down in the process. And it's up to you. Right away, we already know we can evaluate this since it doesn't need to be integrated. However, this on the right-hand side, we will need to simplify and figure out how we integrate x cosine x from x equals 0 to x equals pi. You may notice again, a product of an algebraic expression and a trigonometric function. So we should probably be using integration by parts once more. Okay, well, at this point in time, you can kind of see that because I had an x squared, I'm going to need integration by parts twice. So just imagine if I had started off with x cubed. This process would probably be needing to happen 3 times. Now, don't forget that this 2 is multiplying this whole integral, and this integral, through integration by parts, is getting replaced with 2 terms. And so they both need to be multiplied by 2. U and v, which needs to be evaluated from 0 to pi, and the integral v du, which also needs to be integrated from 0 to pi. So you could keep this 2 factored out, or you can choose to distribute that 2 as you go through integration by parts multiple times. Now here you may find it easier if I do choose to distribute. And notice that this first term is evaluated from 0 to pi. This second term is also evaluated from 0 to pi. And this integral is evaluated from 0 to pi. So actually, by the time I have found this last antiderivative, I can say that the entire expression will need to just be evaluated from 0 to pi. I could actually write this entire expression with a single bar at the end, 0 to pi, or put the entire thing in square brackets and evaluate from 0 to pi. But it might be just easier to work with this one piece at a time. This first expression, x squared cosine x evaluated from 0 to pi. Well, the good news here is when we plug in x equals 0, the whole expression equals 0. And cosine of pi is just equal to negative 1. So this will evaluate to being pi squared. Now, for this next piece, 2x sine x, I'm going to plug in pi and I'm going to plug in 0. But sine evaluated at pi and sine evaluated at 0 are both 0. So when I evaluate that expression from 0 to pi, I just get 0 minus 0. Now this last one I have cosine again, and I can evaluate that from 0 to pi, and I can factor that 2 out. Cosine of pi minus cosine of 0. Well, that'd be negative 1 minus 1, negative 2 times 2, so that just gets me minus 4. And the final answer here is pi squared minus 4. So integration by parts, you do have some choice on how you wish to show all of your calculation. The moment that you do integration by parts once and you have uv, if you want to, right away, you can turn that into a value by plugging in 0 and pi and be done with that portion. And then move on to your integral. And in this case, we had to apply integration by parts twice. So we'd end up with another uv. That middle term, we could go ahead and evaluate that from 0 to pi and get a value and be done with that. And then work on our next integral. So integration by parts, when it has to be multiple times like this, you could be just evaluating the components that are from that uv part of the formula, get that into a value and just work one spot at a time. Or if you wish, you can just try to complete all of the integration by parts operations here and look for that final value at the end. But you should end up with the equivalent value. All right, and if you're still following this far through the video, let's take a look at just a weird, atrocious example of integration by parts. Something that the first time you encounter may seem a little bizarre. Let's call this the strange case of the integral of e to the x sine x. All right, well, let's just see what makes this so strange here. At first glance, sure, it's a product of two functions, e to the x and sine x. Now these are both pretty far down the bottom of the list of good choices for you. In fact, they're probably some of the worst choices for you. If you let u equal sine x, our next integral, du, is going to be cosine x. Is that going to improve things? Probably not much. And it's even worse if we let u equal the function e to the x. Using integration by parts, our next integral is going to have du equal to e to the x again, and that's not going to make anything easier. So it's only just slightly better that we choose u equals sine x, and we let dv equal e to the x dx. Sure enough, we can find that derivative du and that integral to get v, and we get a new integral. Okay, well, that didn't look much improved. We were starting off with a problem involving e to the x sine x, and now we have a problem involving e to the x cosine x. I'll write that one more time, but I'll take away all the fancy colors. Because this time around, we need to use integration by parts again. So I'll have to change some colors here. We'll have to make sure our u is equal to cosine x, since it's the better choice for derivatives. Derivative of cosine x being equal to negative sine x. And dv is going to be our e to the x. Well, let's trust that this is still the preferred way to choose our u and dv and give this another go. And be careful with that minus sign. That negative sign is going to be distributed to the uv, but also distributed to the minus the integral of v to u. So we'll have minus uv plus the integral of v du. All right, isn't that pretty much the same integral we started with? We've got the integral of negative e to the x sine x. We start off with the integral of positive e to the x sine x. So it looks like we could be at this all day. But remember that this first line here is equal to every line afterwards. So if we take the expression that we started with, and we'll write that on the left-hand side of our equation again, and we take this last line and write that down as the expression on the right-hand side of our equation. With it written this way, we can really start thinking about this as an equation with some expression that we want to solve for. It's this expression here in yellow that we want to solve for. We want to solve for that so we get an expression that doesn't involve an integral. We have exactly that same expression here on the right-hand side. Now let's treat that as if it was just maybe some quantity. If we have a quantity here and the same quantity subtracted on the right-hand side of the equation, we can add those two quantities together. We'll simply just add this quantity on the right-hand side, so long as we do the same thing to the left-hand side of this equation. And that's just really a property of any good old equation, the addition property. As long as we add the same thing to both sides, we have an equivalent equation. Well, anytime we have a quantity plus another one of itself, we have two of that quantity. So on the left-hand side, we have 2 times the integral that we wish to find an expression for. On the right-hand side now, we have an expression that doesn't involve an integral. Well, that's great. In order to get this quantity in terms of an expression, we can divide both sides by 2. And there we go, we actually have an expression. Now, of course, since this is an antiderivative, the antiderivative we've just found is one particular antiderivative. We'll still need to add our constant of integration, and we could write this as a nicely factored expression. And therefore, the general antiderivative of e to the x sine x is e to the x over 2 times sine x minus cosine x plus c. Now this is a very weird example, obviously. We like to use integration by parts to come up with a simpler integral, and sometimes we have to use it multiple times. But here, multiple times means we got the same initial integral that we started with. If that is ever going to happen, then you have to start thinking about this whole problem like an equation. Really just thinking about, hey, this is just the product rule multiple times. The left-hand side equals the right-hand side. If I have an integral that I wish to solve for, then I can simply collect them together. And however many values I have of that integral on the left-hand side, I can divide by that constant to get the answer. Just don't forget your plus c. And there we go. That's kind of integration by parts, going from some straightforward examples to multiple integration by parts, all the way to the very weird case of e to the x sine x. And you can imagine e to the x cosine x has a very similar antiderivative as well. Well, thanks for watching. We'll take a look at some more different techniques for integration in future videos. Thanks for watching, and I'll see you in the next video.